So in this lesson, we're going to learn about how we use parallel lines when they are given in proofs. We've already discussed briefly what we know when lines are parallel, but let's review it. What we know is if we have two lines, and we know that they're parallel, so I'm going to use some lowercase letters here to represent the lines, but usually they'll be given the usual way in proofs. Let's say I know that L is parallel to M is given. This is the symbol for parallel. It looks like two little parallel lines, a little bit like an 11, but you wouldn't put the strokes for the 11 that close to each other. So if I tell you that L and M are parallel, and then we cross these two lines with a third line called a transversal, and the four angles here, 1, 2, 3, 4, the dotted ones are congruent and the triangle ones are congruent because they are vertical angles. These four angles here are copied down to here. So these must be congruent to these as they slide down and match up. So this angle will be congruent to both of these, this angle will be congruent to both of those, and so on and so forth. And so when we're given parallel lines, you can deduce congruent angles. You can also deduce supplementary angles, but we'll look at that later. That's not as important for doing triangle congruence proofs as that we can get congruent angles. Because remember, we can use congruent angles in an SAS or an ASA congruence argument. Now, typically when you're doing these proofs, almost always in fact, you're not given this full picture. You don't have, here's the complete parallel line, here's the complete parallel line, here's this crossing all the way through it, and you have all 8 of these angles. Usually you're given just a piece of this. And there are two very important configurations that you need to be able to recognize in doing proofs. These are far and away the most important. They're the most frequent. The first is when you have a Z or an N shape. So maybe I'll be given something like this. Oh, as an aside, I should have said it up here. When we are given parallel lines in a diagram, my way of marking that they're parallel is I put little arrows next to them. I don't use tick marks. Tick marks indicate congruence. These arrows are supposed to remind us these are going in the same direction. They are parallel lines. This is how I will mark in diagrams that things are parallel. So let's say I know in this Z shape here that these lines are parallel. Well, if I look at this Z shape, this is hiding up here in my larger picture. And so I know that this angle here, angle 1, and this angle here, angle 2, have to be congruent. And the name for this pair is alternate interior angles. This is the most common configuration you'll see when you're dealing with parallel lines and proofs. So if, let me call these L and M again, these lines. If L is parallel to M, then angle 1 must be congruent to angle 2 by alternate interior angles. And I will always abbreviate it like that. In flowcharts in your proofs, you would write this like this. L is parallel to M is given, and then I may deduce angle 1 is congruent to angle 2 because of the alternate interior. They are alternate interior angles. So given the parallel lines, you may deduce that these angles in this configuration are congruent. Now this configuration, this Z shape, can look different. You can look like an N. This would still be alternate interior angles here. It can be a mirror image N, so it could be something like this. This would still be alternate interior angles. You can even have something really stretched out like this. These here would be alternate interior angles, because if you complete the picture, if I imagine these lines continuing, you can see now they're they are interior angles and they're on different sides of this transversal coming down here. So this Z shape or N shape is very common when you're doing triangle congruence proofs. The other very common one, but nowhere near as common as alternate interior angles, is corresponding angles. And that's when you have something that looks a little bit like an F. It might be mirror image or might be on its side. But these angles here, there, and there are corresponding angles. So if you're given that these are parallel, this is L, this is M, here's my transversal. If you imagine these lines extending out so you get the full picture with all 8 angles, this angle and this angle are in the corresponding position. So this F shape here is somewhat common, and these would be called corresponding angles. And we can see the same thing that we did up here with the alternate interior angles. If L is parallel to M, if that's given, if I number these angles, let's say I call them 3 and 4, then I may deduce angle 3 is congruent to angle 4. And here the reason is because they are corresponding angles. So these are the two types of shapes, this Z or N shape or this F shape, that you want to look for if you're given parallels.
The parallels would be the top and bottom of the Z, or the beginning and the ending of the N shape, or the parallels are the 2 crossbars on the F going across like this. And again, the F doesn't have to look like a letter F. It could be on its side like this. These would be corresponding angles. So there are different ways you can look for the corresponding angles pattern. Let me do an example. So here's our first example. We're given AB is parallel to CD and E is the midpoint of BD. So I'm going to follow my usual pattern, marking my givens when I do triangle congruence proofs. We're still doing triangle congruence proofs. It's just now we have a new ingredient, which is these angles that we can work with given from parallels. So AB is parallel to CD. I will mark that with my parallel symbols. That's a reminder that I know that that's given as parallel. And E is the midpoint of BD. So there's BD. So I know these are congruent. And I want to prove E is the midpoint of AC. And it's pretty clear here that I'm going to want to try to prove these two triangles congruent, and that will tell me that AE and EC are the same, and that will tell me E is the midpoint of AC. In fact, if I want, I can start with the end. I can say, all right, I'm going to go for AE is congruent to EC. This is the end of the proof. It's going to be corresponding sides of my congruent triangles, and then this will tell me E is the midpoint of AC. I know that's where I'm going. This is the definition of midpoint. So I need to get a pair of congruent triangles. Using SAS or ASA or something that will let me get AE and EC. One thing that has not changed is that we still need 3 congruences going into triangles being congruent. That has not changed. It's exactly the same as before. If I look up here, I only have 1 congruence. Under no circumstances, let me stress this, you may never have the parallels going directly into triangle congruence. That is wrong. It still as before, you need congruent sides, congruent angles in the SAS or ASA or SSS pattern going into this. This is incorrect. You should never have parallels going directly into triangle congruence. It's the same as before. But what I do know from what I was thinking about earlier is that parallel lines give me congruent angles. And so I'm going to look for a Z pattern or an F pattern that will give me angles that will be helpful in getting triangle congruence patterns. If I look, there's 2 Z's here. Here's one Z that goes like this, goes across this way, and then back up like that. If I trace that Z, it goes A to B to D to C. And the 2 angles are there and there. Those would be alternate interior angles because of the Z pattern. There's another Z that goes the other way. Goes B to A to C to D. There's another Z pattern. But these angles
although they are congruent because of the alternate interior angles pattern, they're not going to be very helpful in doing triangle congruence, because I'm going to be getting, I need to have information by this pair of congruent sides. If I'm going to do an SAS or an ASA pattern, the angles have to be next to the side. So I'm going to use this pair. I'm going to say these angles are congruent. Now I need one more pair of congruent angles or congruent sides, and our old friend vertical angles helps us out. And this completes an angle side angle pattern. I have ASA in this triangle, and I have the corresponding ASA pattern in the other triangle. That shows that the two triangles are congruent. It's going to be an ASA proof. So much of this is the same as what happened before. We have the vertical angles, angle BEA and angle DEC. They're vertical angles. We have BE and DE. That's the pair of sides. And how did I know that those were congruent? Because of the midpoint statement. And the last thing is this pair here, angle B and angle D. And I demand you may not use congruent angles in a proof that come from parallels unless you put above it the parallel lines that gave it to you. So it must look like this. AB parallel to CD given, and then that tells me that angle B and angle D must be congruent because of this Z shape, and we have, those are alternate interior angles. That's a little bit sloppy, I apologize. And then finally, to complete the proof, I need to give proper names for these triangles. If I follow the tick marks around, this triangle is triangle BEA, and the other triangle, if I hit the tick marks in the same order, goes DEC. And there's our first proof working with parallel lines. This is the only thing that is new here, is that because the lines are parallel, those alternate interior angles are congruent. Everything else here is a familiar angle side angle triangle congruence proof. Let's do one more example. Excuse me. So I'll mark my givens. WU is parallel to VX. So I use my arrows to mark parallels. UW is congruent to VX. Oh, so these are also parallel. I don't know why I changed it from UW to WU. So there I have parallel and congruent. XW is congruent to XY. And I want to prove that UX is congruent to VY. So if I can prove that these triangles are congruent, this would follow by corresponding parts. So we know that's how it's going to end. There's only two triangles here. It's going to be those. And you can see, here's Z shapes. There's my parallels, here's a Z shape. But this Z shape here is not very helpful for doing a proof, because it would tell me this angle and this angle have to be congruent. But that's no help. This angle is not even inside one of my two triangles. And so I'm not going to try to use that Z pattern. There's another Z pattern here, U to X to V to Y. The problem with that one is you're not even told that UX and VY are parallel. And if you're going to use a Z pattern in a proof, you have to be told that the beginning and the end of the Z are parallel. Otherwise, you cannot use these alternate interior angle ideas. Now, I am given parallels, so presumably I'm going to use angles somehow in this proof. You're not going to be given parallels and not work angles in somehow. And then I think, wait a second. Here I have two pairs of sides. That leads me towards, that's SS. And I know the parallels have to give me angles. So this is definitely going to be an SAS proof. The parallels are going to give me some pair of angles someplace that's going to probably finish an SAS pattern. And if I look, there's an F hiding here. Let me color it a different color so you can see it. I don't know how this color will show up or not. Not very well, but I can darken it. Right there is a weird looking F shape. There's the F. Looks like this. And when we have these bars in the F as parallel, then these are corresponding angles. And they must be congruent if those lines are parallel. So that's going to be this angle here, which for convenience I'm going to label angle 1, and this angle here, angle 2. Because these are parallel, that means that this angle and this angle must be congruent, and that finishes my SAS pattern. Let's look at how it would look if we wrote up the proof. So I'm going to write up my SAS argument. Both my pairs of sides are given. So that's one pair of sides. Here's my other pair, XW. I'm just recopying the givens down here. Don't have to think too hard about that. This is given, this is given. Remember, you're not going to put this directly into triangle congruence. The parallels never go directly to triangle congruence. Instead, you use the parallels given to create a pair of congruent angles. In this case, it's angle 1 and angle 2. And these are not alternate interior angles. That's the Z shape. These are corresponding angles. The F shape is corresponding angles. So I've detailed my SAS pattern. So now that I've told you that I have SAS, I may deduce that the two triangles UWX and VXY are congruent by a side angle side argument, and then therefore what I'm trying to prove, UX and VY, are in fact congruent because UX and VY are corresponding sides of the two